Today we have two topics. The first one has to do with the shared electrons in a shared electron bond or a covalent bond not being always shared equally. That's a concept known as polarity. And then we're going to talk about the shapes of molecules, and I'm going to give you a theory that's been developed to help make accurate predictions about what the shape of a molecule is going to be like. When the electrons in a covalent bond are not shared equally, that bond is said to be a polar bond. The tool that we use to determine how unequally the bond electrons are being shared is electronegativity. Electronegativity is a characteristic of certain atoms. Every atom has its own ability to draw the electrons that are in a shared bond or a covalent bond to itself. That ability is reflected in this number called electronegativity. The highest electronegativity is fluorine. And in general, things up in the fluorine corner tend to have the highest electronegativities. And as you get farther away, down in the other corner where cesium and francium are, you find very low electronegativities. It's the difference between the two electronegativities of the atoms in a bond that determines, in part, if it's going to be called a polar bond or not. There are other factors, but we're going to look primarily at electronegativity difference as a way of determining the polarity of a bond. The difference in electronegativity doesn't determine polarity, but in fact measures what's called the ionic character of a bond. If a bond has high ionic character, that means it's more like an ionic bond. In fact, very high ionic character means it is an ionic bond. Low ionic character means it's very much unlike an ionic bond. Now, recalling that ionic bonds are when electrons are transferred from one atom completely to the other atom, that means this is a real extreme case of unequal sharing of electrons. So you can think of an ionic bond as just a special case of a covalent bond, really, where the electrons are shared so unequally that they're said to have been transferred. This chart gives us a way to describe ionic character in terms of electronegativity difference. So on the x-axis here, on the horizontal axis, we have electronegativity difference, or delta En. And on the vertical axis, we have what percent of being totally ionic is that bond. Like, for example, 50% means it's like half ionic, roughly. So what does that mean? Well, the boundaries are pretty fuzzy here. We shouldn't have straight lines here. We should have kind of blurry lines. But in general, we can say that if something has less than 5% ionic character, that's what we consider a non-polar bond. And we consider the electrons in that bond to be pretty much equally shared between the two atoms on either end of the bond. If we have ionic character that's like higher than 50%, well, that's an ionic bond. That's really not even a covalent bond. So in the middle, roughly from 5% to roughly 50%, we have this region where we have covalent bonds, but their unequal sharing is such that we could call that a polar bond. Let's go back to the last chart and figure out what that means in terms of electronegativity difference. This is approximately 5% ionic character, and that's the lower end of the range that we call a polar covalent bond. If you trace over until you hit the line and go down, you'll find out that it's approximately 0.5 electronegativity difference. That's the low end of our range of values that we would call polar covalent bonds. 50% ionic character and higher we consider to be a ionic bond. So if you trace this over, you come out to somewhere around 1 3/4 to 2. That's about the range. So we could roughly say that between 0.5 and 2 electronegativity difference is what we call a polar covalent bond. There's actually more to it than just electronegativity difference, but you'll get pretty close by using that estimate. So let's categorize these bonds using electronegativity difference as polar covalent, nonpolar covalent, or ionic. First of all, let's take a look at an OH bond. O is 3.5, H is 2.1. So the electronegativity difference for this bond is 1.4. So 3.5 minus 2.1. What does that make it? Well, that's solidly in that range between 0.5 and about 2. So we would call this a polar covalent bond. NH. Here's nitrogen, it's 3. Hydrogen is 2.1, remember? So the electronegativity difference is the difference between 3 and 2.1, or 0.9. Well, that's right in that range too. So this is also a polar covalent bond. CH. Carbon is 2.5. Hydrogen is 2.1. The electronegativity difference for a CH bond is only 0.4, and that's just a little below the range that we would call a polar covalent bond. So this is a nonpolar bond, and we say that the electrons are equally shared in this bond. Sodium and fluorine. Well, fluorine's a 4, it's the highest one. Sodium's 0.9. The electronegativity difference is 3.1 for this bond. Well, that's way higher than what it should be to be a polar covalent bond. This is in fact what we call an ionic bond, and that's no surprise to you because it's a metal and a nonmetal. Now we're going to turn our attention to predicting the shapes of atoms. There are some cases where this is really easy. Compounds that contain only 2 atoms must be a straight line. So H2, for example, there's the Lewis structure, H2 bonded to an H. That's got to be a linear molecule. There's got to be a straight line. Or HCl, Lewis structure looks like this, straight line. Or N2, triple bonded like that. There's only 2 atoms. In all these cases, it has to be a straight line because 2 points or 2 atoms, in this case, determine a line. When they get more complicated than that, we make use of a theory called VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory basically says this: valence electron pairs are repulsive to each other because they're all negatively charged and like things repel one another. So these valence electron pairs are going to stay as far away from each other as they possibly can, and so that'll cause the molecule to arrange itself in a way that keeps these electron pairs at a distance from one another, and that allows us to predict what their shapes are going to be. Now, to get you familiar with the idea of this, we're going to go to a little simulation utility, and I'm going to build all these shapes by adding electron pairs to a central atom. And this simulation is written, it's programmed to automatically determine the geometry using mathematics that would exist for every combination of electron pairs that we're going to study. And then we'll come back and actually look at real molecules and apply what we've learned. We're going to use this little simulation device to build these molecule shapes from VSEPR theory. Down in the lower corner here, you can see the shape's name as it's being built. I'm adding regions of electron density. They're just globs of electron cloud, basically, at this point. And you can see the different shapes being formed. We had linear. This is trigonoplanar. You can see that it's flat and it's triangular, and so it's called trigonoplanar. This next one is tetrahedral. The outside points of these little globs would form the vertices of a tetrahedron, and that's where the name comes from. And it's symmetrical in all dimensions, so no matter which one you turn up, it always looks the same. This is called a trigonal bipyramidal shape, and its vertices are those of 2 pyramids with a triangular or trigonal base that share the same base. We'll talk more about that shape later. If I have 6 regions of electron density, 6 globs, I've got what's called an octahedral shape. This is like the tetrahedral. It's symmetrical in all directions, and the outsides of the globs are the vertices of an octahedron. Okay, so what we saw was that when you have only 2 pairs of electrons, and they have to arrange themselves, according to VSEPR theory, they're going to create a linear molecule. So 2 pairs of electrons, or 2 outside atoms if both of those pairs are a bond, it's going to make this linear shape. When you arrange 3 pairs of electrons, they're going to make a trigonal planar shape. They're going to get 120 degrees from each other and lay flat in a plane. If all 3 of the electron pairs are bonds, well, then you're going to have this trigonal planar molecule here. A tetrahedral shape is formed when you have 4 regions of electron density. And remember, they have a bond angle of 109.5 degrees. If they're all bonds, then you have this tetrahedral shape. If you have 5 regions of electron density, then you get this trigonal bipyramidal shape. The trigonal bipyramidal shape has 2 bond angles. It has this equator that we see right there that's very much like a trigonal planar. It's got 120 degree bond angles. But then 90 degrees up from that and 90 degrees down from that, we have axial bonds. This is very much like the axis and equator on a globe. So 90 degrees from the equatorial plane, we have 2 bonds, and then 3 bonds 120 degrees from each other in the plane of the equator. If they're all bonds, then we have a trigonal bipyramidal molecule. If you have 6 valence shell electron pairs trying to orient themselves as far apart as they can in space, you end up having this octahedral shape where all the bond angles are 90 degrees, and you've got sort of this cross here in the central plane, and then a vertical up and down, sort of like with trigonal bipyramidal. If all of the electron pairs happen to be bonds, then you have an octahedral molecule, an 8-sided molecule, if you connect all the points. So how can we predict shapes? Well, there are a couple of ways to go about it. If you're good at spatially visualizing things, you can draw the Lewis structure and just think about how these things would have to be organized, and then pick a molecular shape. Otherwise, if you're not very good at visualizing things and you just want to, get the right answer, I can give you a little cheat code that I'll introduce as we develop this thing to help you remember that. But all of this starts with Lewis structures. You have to draw a Lewis structure. Once you've drawn the Lewis structure, you should count the regions of electron density that exist. Now, what counts for a region of electron density? One thing that counts is any kind of a bond is one electron density region. Single bond, double bond, triple bond. They all count the same. And the other thing that counts as a region of electron density is a lone pair. So a pair of dots in Lewis structure. Once you know how many regions of electron density are there, you can pick one of the basic VSEPR shapes, either linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. The molecular shape is given by the location of the atoms that are there, but the VSEPR shape is influenced by all of the electron pairs. So water is a good example of what I'm talking about. If you draw the Lewis structure for water, you find that you have 4 regions of electron density. 2 of the regions are lone pairs, and 2 of the regions are bonds. But all 4 of those regions are repulsive to each other, whether or not there are bonds there. So if you think about that oxygen atom as being in the center, it's in the center of a shape that's arranged tetrahedrally. So we would have a bond here, and 109.5 degrees away we'd have another bond. This would not be linear because over here we got this lone pair, and then back here we have this other lone pair sticking off back into the page. And so even though there are only 2 outside atoms, the fact that these repulsive lone pairs exist causes this shape to be bent, not a straight line like you'd see with only 2 outside atoms and no lone pairs. Let's look at some examples and build up our knowledge of shapes by using examples. So first of all, we're going to look at 2 regions of electron density with no lone pairs. CO2 would be an example of this. If I draw the Lewis structure for CO2, we've done this before, we know what we come up with. Now to predict these shapes, we're not looking at the outside atoms, we're looking at the central atom. So if I look at this central carbon, I find that I have 2 regions of electron density. One there, that double bond, and the second one is there. If I have 2 regions of electron density, they're going to arrange themselves in a linear shape. They're going to get 180 degrees away from one another, and I'm going to have a linear molecule. So 2 regions of electron density with no lone pairs. Best way they can organize themselves to get those electron pairs as far away as possible from one another is to have a linear shape. As we add 2 bonds to the central atom, we can see that the angle that we get after it settles down here is 180 degrees. Now, here's another way we can think about this. I can think about this as an AB2 code molecule. A stands for the central atom, B stands for the outside atom, and we're going to find later on that you can have some lone pairs in the central atom, and we'll call those E's. But if you can just look at the Lewis structure and recognize I have 1 central atom, 2 outside atoms, and no E's, no lone pairs, that's going to always be a linear molecule. Let's take a look at this one. This is BCl3. If you draw the Lewis structure for BCl3, and you remember that boron has only a full sextet and not a full octet, I'm going to leave the lone pairs off of the outside atoms because they don't really matter at this point. you will recognize that you have three regions of electron density. Those three regions of electron density are all three bonds. Well, three regions of electron density arrange themselves at 120-degree angles, kind of like what I've drawn here, and the shape is going to be a trigonal planar shape. To a linear, we're going to add another region of electron density, a bond in this case, and we can see that what we get is this flat molecule with 120-degree bond angles called a trigonal planar. What's the cheat code? AB3. If you can remember one central atom, 1A, and three outside atoms, 3 Bs, that's always going to be trigonal planar. Then you don't have to think about the shape and visualize it in your head. Three regions of electron density with one lone pair. NO2 is an example of what I'm talking about here. If you draw the Lewis structure, you'll end up with this. Single bond to an O, double bond to an O, and a lone pair. Again, I'm leaving off the lone pairs on the outside atoms. They're there, but they don't influence geometry because we're only looking at the central atom. When we do look at that central atom, we find that we have three regions of electron density, two bonds and one lone pair. Three regions of electron density are arranged in a trigonal planar relationship. So we're going to have a 120-degree angle here, and what we've got is the nitrogen bonded to an O here, bonded to an O here, and then up here we've got a lone pair. That lone pair doesn't have anything on the end of it, it's just a pair of electrons, but because it's repulsive, it's going to keep these oxygens from being in a linear shape that you might expect and force them into this 120-degree angle. The molecular shape is what we call a bent 120. It's a bent molecule and has a 120-degree angle in it. Starting with this trigonal planar molecule, we're going to remove one of the bonds and replace it with a lone pair to model what we have with the nitrite ion. Because the lone pair is there and it's repulsive, it still has an influence on the shape of the molecule. We've got a 120-degree bond angle and not a linear molecule like we'd have normally with one inside and two outside atoms. When we remove the lone pair, we can see the shape of the molecule, and it's definitely influenced by the lone pair that's invisible to us now. What's the way that you can remember this without thinking about shapes? Well, this molecule is an AB2E1 or AB2E molecule. Central atom, two outside atoms, one lone pair. And AB2E, you can just always think about that as a bent 120-degree angle molecule. Next, let's look at four regions of electron density with no lone pairs. CH4 would be an example of this. If you draw the Lewis structure for CH4, very simple, that's what it is. Four regions of electron density are going to arrange themselves in that tetrahedral pattern. And here's how we draw that. We draw two of the bonds right in the plane of the page that we're writing on. And remember, there's a 109.5 degree angle between these two bonds. And then one of them actually isn't in the plane of the paper. It comes out a little bit. And so the standard way to sort of draw that is to fill in this triangle. It looks like it's getting bigger. And then one looks like it's sticking into the page. And the standard way to draw that is to make a triangle that looks like it's getting smaller out of dashed lines. So this is how this thing is actually arranged. The hydrogens are on points of a tetrahedron, and the carbon's in the center. This shape is a tetrahedral molecule. That's the molecular shape. We're going to add another region to a trigonal planar, and now we have a shape whose 4 points are the vertices of a tetrahedron. This is called a tetrahedral molecule. The molecule could be thought of as an AB4. One central, four outside, no lone pairs. And those are always tetrahedral. Four regions of electron density when one of them is a lone pair. Ammonia is an example of that. If you draw the Lewis structure for ammonia, this is what you end up with. Looking at the central nitrogen atom, you have four regions of electron density. There's a lone pair, and then there are three bonds. Four regions of electron density always arrange themselves in that tetrahedral shape. So here's my central nitrogen. I'm going to put the lone pair up here. So that's 109.5 degrees away from a hydrogen. Then 109.5 degrees away from that hydrogen is going to be another hydrogen down here. and then 109.5 degrees away from both of them is going to be another hydrogen that's sort of way in the back of the molecule. This molecule is a pyramid, and the pyramid has a triangular base. So we call this a triangular or a trigonal pyramidal molecule. Starting with a tetrahedral molecule, we'll remove one bond and replace it with a lone pair. We see that the lone pair still influences, and that means that we don't have a flat trigonal planar, but we have a trigonal pyramid. Here it is without the lone pair. So you can either visualize this, or you can remember that when you draw the Lewis structure, you have an AB3E1 or AB3E molecule. One central atom, three outside atoms, one electron pair. 4 regions of electron density, 2 lone pairs. We've actually done this shape already. It's oxygen bonded to 2 hydrogens, 2 lone pairs. So 4 regions of electron density, as always, are going to arrange themselves in a tetrahedral fashion. So my O is going to go there. I'm going to have like a lone pair here sticking back into the paper. I'm going to have a lone pair here that's sort of sticking out of the paper. And then I have an H here, and I'm going to have an H here. And the bond angle between those is 109.5 degrees, but it's actually not, because this lone pair and this lone pair are spread out more than they would be if there was an atom on the other end restricting where they go. And so that makes them even more repulsive than a bond. So because those lone pairs are there, both of them, and there's so much extra repulsion there, this actually gets squeezed down to about 105 degrees. And so the molecular shape here is bent, but to distinguish it from a bent 120 and to give an idea of what its shape really is, we call it a bent 105. Starting with this trigonal pyramidal, we'll take away a bond and add another lone pair. Now we've got this bent molecule. Definitely the lone pairs are still influencing it, so it's not linear. The angle it says here is 109.5, but actually because the lone pairs are so repulsive, it's squished together a little bit more, and this is really a bent 105 molecule. So what kind of a molecule is this? This is an A, B2, E2. 1 central atom, 2 outside atoms, 2 lone pairs. 5 regions of electron density with no lone pairs. PCl5 would be an example of this. There's P in the middle. 5 chlorines arranged outside of it. There are no lone pairs on this molecule, except on the outside atoms. 5 regions of electron density arrange themselves in that trigonal bipyramidal shape. Here's how we can draw that. It's kind of a standard way to do this. I'll put the phosphorus in the center, and then I'll draw this triangle that sort of looks like a knocked over equilateral triangle. At the points of it, I'm going to put my equatorial atoms. So 3 chlorines on the outside. I can even sketch my little bonds in there. And then my 2 axials, put one up here, and then peeking down from underneath that central plane is my other one. So I have 120 degree angles between the chlorines that are in the equator inside that triangle, and then I have one up and one down at 90 degrees from that plane. So this is a trigonal bipyramidal shape. It's called trigonal bipyramidal because it's 2 pyramids, and they both have a triangular base that they share in the middle. To a tetrahedral geometry, I'm going to add a 5th bond, and I can see I get this shape that's called a trigonal bipyramidal. The bond angles are 120 degrees in the equatorial plane, the plane of the equator, and then the bond angles to that equator are 90 degrees each. Trigonal bipyramidal shape comes from an A-B-5, 1 central atom, 5 outside atoms, no lone pairs. 5 regions of electron density where one of them is a lone pair. SF4 is an example of that. If I draw the Lewis structure for this, this turns out to be one of those expanded octet things where the structure doesn't have enough electrons, and so we have to put an extra electron pair on the sulfur. So now we have 5 regions of electron density, bond, 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 and a lone pair. 5 regions of electron density are always going to arrange themselves in that trigonal bipyramidal way. So my sulfur is going to go in here, and I'm going to have one region up, one region down, and then one region facing each of the three equatorial plane corners. Now, because the bond angles aren't all equal here, I have to think about where is there the most room for this lone pair, because remember, it spreads out more. It's more repulsive than the other electron pairs that are involved in bonds. And since the bond angles in the equator are 120 degrees apart from each other, and the bond angles in the axis are only 90 degrees away from three bonds, there's more room in the equator. And so that's where that electron pair is going to go. So with my electron pair taking up one of these equatorial spots, my fluorines are going to go in the remaining corners and on the bottom. This shape is called a seesaw shape. It's not easy to see here, but with a model it would be more easy. This fluorine and this fluorine represent sort of the base of the seesaw. There's the fulcrum, and then here's where the one kid sits, and here's where the other kid sits on the seesaw. So this is a seesaw that's set on end. Try and draw it a different way. So here's a little fluorine coming in. There's a fluorine going into the paper. Here's my sulfur, and then I have a fluorine here, and 180 degrees another fluorine. So this is the seesaw. That's where that name comes from. So seesaw-shaped molecule. It's also called an asymmetrical tetrahedron, but seesaw is easier to remember and makes more sense. Starting with this trigonal bipyramidal, we'll take away a bond and replace it with a lone pair. And this gives us a shape that's definitely still trigonal bipyramidal for the valence shell electron pairs. When we take the lone pair away and start to manipulate it a little bit, you can see where its name comes from. This molecular shape is called a seesaw molecule. Looks like a kind of a floppy seesaw, but it's behaving like a child's seesaw. And what kind of a molecule did this come from? Well, this is an AB4E1, or AB4E. One central atom, four outside atoms, and one electron pair on the central atom. 5 regions of electron density with 2 lone pairs. ClF3 is an example of that. Central chlorine, and then 3 outside fluorines. The chlorine doesn't have a full octet, so we have to put one there, and then this ends up actually being one of those expanded octet deals where we have to have another lone pair. So we end up having 5 regions of electron density. 3 of them are bonds, and 2 of them are lone pairs. So 5 regions are going to arrange themselves in this trigonal bipyramidal shape. So I'll sketch that out. Here's my chlorine in the center. And we've already figured out now that the equator is where there's more room for lone pairs. So that's where they're going to go. One of the lone pairs will be there. One of the lone pairs will be there. And then there'll be a bond to a fluorine there. And then the axial bonds will both be to fluorines. And so we end up with a molecule that's flat. And it's shaped like a T. So we call this a T-shaped molecule. I'm sure there's a fancy name for it. I don't know what it is. T-shape makes sense to me. Starting from this seesaw molecule, we're going to take another bond away and replace it with a lone pair. Still have a trigonal bipyramidal geometry here, but now with 2 lone pairs, the actual molecule shape is going to be a little bit different. When we take away the lone pairs, it's very clear to see this is shaped like the letter T, and that's where its name comes from. It comes from this molecule, A, 3 B's, 2 E's. It is possible to have 5 regions of electron density with 3 lone pairs. I31- is an example of that. Iodine, 2 outside iodines, and with this shape you end up having 3 extra electron pairs on the central atom. So you have 5 regions of electron density, 3 lone pairs, and 2 bonds. In that trigonal bipyramidal arrangement, remember there's more room in the equator, so here's what you end up with. Iodine in the center of that equatorial picture, and then I'm going to have a lone pair sticking off this way. I'm going to have a lone pair sticking off towards that corner. The third lone pair is going to be sticking off towards that corner, and I'm going to go up to an I here and bond down to an I here. And so I end up with a linear molecule. It's just one straight line like that. Starting with this T-shaped molecule, I'm going to remove a bond and add a lone pair. Now I have 5 regions of electron density. 3 of them are lone pairs. So it's a trigonal bipyramidal, but it's linear in shape. What kind of a molecule makes linear? Well, an AB2 does, but an AB2E3 also does, and that's what we've got here. 6 regions of electron density with no lone pairs. Sulfur hexafluoride is an example of this. If you draw the Lewis structure for SF6, you end up with 6 outside atoms, no lone pairs. If I look at how many regions of electron density are there, well, obviously there are 6, and they're all bonds. 6 regions of electron density are going to be arranged in a octahedral shape. Here's how I can draw that. Just like I drew a knocked over equilateral triangle, I'm now drawing a knocked over square, which kind of looks like this rhombus thing. I'm going to put a sulfur in the center. My fluorines are going to go on the 4 corners, kind of like an equator here. There are my bonds. And then up from here, I'm going to put a fluorine, and then sticking down here goes the other fluorine. This is the octahedral molecular shape. All the fluorines, if you connect them all up, you are going to make an octahedron. That's where the name comes from. All the bond angles are equal here. They're all 90 degrees from each other. To a trigonal bipyramidal, I'm going to add a 6th region of electron density. This gives me this symmetrical shape that has 90-degree bond angles everywhere. This is an octahedral geometry because its points are the vertices of an octahedron. And the kind of molecule that makes this is, of course, an AB6. 6 regions of electron density with 1 lone pair. BRF5 is an example of this. If I draw the Lewis structure for this, I end up with 5 outside fluorines, and then when I count up my electrons, I found out that I won't have enough, so I end up having to put another electron pair on the central bromine. Here are my regions of electron density. 1 lone pair and 5 bonds. Now when I think about my knocked over square here with bromine in the center, it really doesn't matter where I put that lone pair because all the bond angles are the same. They're all 90 degrees from each other. So this is how I'm going to draw it out. Put my 4 fluorines that are sort of in the equator there, and then I'm going to put 1 up here, and then down here I'm going to put that lone pair. What we end up with is a pyramid that has a square base, and so we call this shape, this molecular shape, a square pyramidal shape. To see 6 regions with 1 lone pair, we're going to take this octahedral molecule, remove 1 bond, and replace it with a lone pair. The electron geometry is still octahedral, but now when we look at the shape of the molecule, it looks like a pyramid that has a square base that's called a square pyramidal. The kind of molecule that makes it is an AB5E. 1 central atom, 5 outside atoms, 1 lone pair. Last one. 6 regions of electron density with 2 lone pairs. Xenon hexafluoride is an example of that. If I draw xenon hexafluoride, I find out that I have 4 outside atoms of fluorine, but then I end up having to put 2 extra lone pairs on the central xenon to make my electron count right. Thinking about my shape, here's my central plane, and I've got 4 fluorines here, and my xenon in the middle. Now I have 2 lone pairs that I got to put in here, and if one of them was already down here, then it makes sense for the other one to be 180 degrees away from that, because remember the lone pairs are more repulsive. So we end up with a flat molecule. If I were to look at this from above, I'd see this. Just a plus sign, basically, with xenon in the middle. So this is planar, and it's square, so the name is square planar. Starting with this square pyramidal, we're going to take away another bond and replace it with a lone pair to show 6 regions and 2 lone pairs. Now what we have is a flat molecule, planar, and its points are on a square, so this is a square planar. And the molecule that produces a square planar is an AB4E2. There are other conceivable molecular shapes, but you can see we're already sort of stretching it. We've got noble gases reacting, and we've got crazy things like I3- to make our point here. So we're going to stop before things get really out of hand and just go with these molecular shapes that we have so far. Now, the shapes are really important because it turns out that if you take the idea of polar bonds and then the idea of shape and put them together, you can start to predict how these things are going to behave when they're around one another, even after the bond has formed. And that makes all the difference in whether it's going to be a solid or a liquid or something that boils at a high temperature or a low temperature. All kinds of things like that depend on molecular shape and polarity. So more about that next time.